It's my pleasure to introduce my friend and colleague, Professor Larry Head. Professor Head is a professor in system engineering from University of Arizona. He just returned to his faculty position from interim dean position at the College of Engineering at State University. He was also the department head at his department. And Professor Head is a well-known researcher in traffic signal control. He has done some of the pioneering work in this field, particularly with traffic signal control with connected vehicle environment. In his early career, he also contributed significantly to one of the well-known real-time adaptive signal control system, road systems, in 1990s. For those people in my traffic science class this semester, we talk about specifically to control optimization of physics, the COP algorithm, and Professor Head was the developer of that algorithm. So if you have questions on that, if I didn't explain clearly, then ask the original developer of this algorithm, and later on be utilized, I believe it's being utilized in the NIST system as well, which he's going to talk about today. So without further ado, please help me welcome Professor.
Great, thank you. Thanks, Henry, for the nice introduction. It's an honor to be here. You know, I'm in the heart and the soul of connected and automated transportation, I believe, and the vehicle technology for sure. So what I wanted to do today was just share some experiences about some application development that we've done related to MITs. I'll tell you what that is, and some work zone stuff we did, and then some emergency vehicle alert that I'm passionate about, and then cooperative safety that we're working on. So now I know here at University of Michigan, everybody knows what connected vehicles are. And at some point in my life, I'm going to take this slide out of my talk. But I'm not ready to do that, because I think it's important we all reflect and remember that this is about cars talking to cars for safety purposes. Right? And I get together with one of my colleagues at the university who's an expert in wireless communication, and he's telling me 5G is fantastic, it's really going to be great, and we can do this, and we can do that, and we can do this. And I'm like, I need cars to talk to cars. And he goes, no, you don't understand, that's not how it works. And I'm like, we need cars to talk to cars. So my point is on this slide is we still have to have cars talking to cars. We like the idea of cars talking to the infrastructure, because when we're in traffic and transportation management, there's so many things that we can do if we get the cars equipped and we get the infrastructure equipped, and we can have these dialogues about safety and mobility and the environment. On both of these slides, when I list the wireless communication, I list DSRC, LTE, 5G, 802.11bd. To be perfectly honest, I don't care, but I'm getting old and I can't wait much longer. So let's get on with it, right? Because getting the wireless technology is going to help us do the wonderful applications. If we keep putzing around with the wireless technology, we're not going to get anywhere very fast. So being able to exchange messages with traffic signals on the roadside, having the information about the map that describes the geometry of the roadway, and being able to use it in making decisions. It's really important in vehicle to infrastructure. It's not so important in vehicle to vehicle all the time. Two vehicles in the middle of nowhere might encounter each other and could have a safety interaction, right? So, okay, so enough for that. One of the things I really like about this technology, and when I got involved back in 2004, was it could be on a car, a truck, a fire truck, a bus, or maybe even a pedestrian, and maybe even a handicapped pedestrian. And this, to us, in the traffic business, is revolutionary. We never knew whether that vehicle that went over that loop detector was a car or a truck. Was it a motorcycle or a Ferrari or a fire truck? Okay, and we did know fire trucks and things with Opticom and such. But we can really start thinking of applications to improve things. So the first application I want to talk about is called the Multi-Modal Intelligent Traffic Signal System. And just for the record, I didn't get to choose the name. ROADS is a much nicer name than MITS, but because it has a nice acronym to it and means everything. But MITS, really, the idea was this is a pool fund project that was sponsored by US DOT and a group of states that got together with their money and said, we really want to find out what the potentials are for traffic control if we have connected vehicle technology. What are the things that we can do? And so the team is a group of us from the University of Arizona. Really good shout outs to Niraj, Altakar, Debashish Das, my PhD students who work tirelessly day and night, and Yiheng knows what that's like to be in the lab and working. I know you still do it here. And then a group from UC Berkeley PATH program led by Kun Zhu, and our champions are the Maricopa County DOT and California DOT, and so it's really important that I acknowledge all of them in the project. But the basic idea behind MITS is this. When we manage traffic in our systems, we typically break the system up into different control sections. And usually this is because the control sections have different objectives. So maybe this section that's up here on the top of this map, okay, and this is just hypothetical, so don't get excited about where the signal spacing and things are. But maybe the operating agency says, you know, I have train tracks that go through there, so I definitely have to worry about freight priority or rail crossings. I really care about my emergency vehicles getting to where they're going safely and quickly, but in this corridor I have a lot of warehouses and I'm going to move a bunch of freight through there. Maybe I'm going to move it as platoons or maybe I'm going to move it as vehicles, right? But I want you to give preferential treatment to them at the traffic signals, and then maybe I want you to coordinate the signals, and then we have a little bit of transit goes through there because people come and go to work at certain times of the day and we want them to use the transit, and then passenger vehicles, and we don't have many pedestrians. But this other section on the other side, maybe this is where there's lots of shopping and schools and activities where there's lots of pedestrians and transit, and we really want to make it a travel-friendly environment, somewhere where they feel comfortable hopping on a bus and going a few blocks and getting off or something, and so the pedestrians and transit, and maybe we want to favor BRT at certain times of the day, and maybe if there's groups of vehicles that get together in strings, we want them to flow through the signals, because we could adapt the signals to do that, and then maybe pedestrians and passenger vehicles, and finally freight. So we can change the order of the hierarchy that's there. And the other thing that's really important in the connected vehicle world, and you guys see this here all the time, is we can finally measure performance in ways we've never thought of, right? And we can do all the traditional things, volume, delay, travel time, throughput, stops, and such. Those are all exciting. We can do it by mode, by movement. So if we have a heavy movement of trucks making a left turn and their flow rate is pretty slow, we can actually assess that that's going on. That would impact how much time we want to give that phase, all right? And then at the bottom, I added a couple more measures that I think are really important, especially if we're talking about moving groups, platoons, or strings of vehicles, called smoothness. And I'm interested in measuring things like time and system, and I'll talk about smoothness again. And so MITS is really, after many, many years of doing adaptive systems and thinking about the different kinds of control that's out there, the pool fund panel that wrote the original RFP some 7, 8 years ago, whenever that was, put together some ideas. So first of all, use connected vehicle data. So we do that, basic safety messages, map, signal request message, signal status message, and SPAT data. Then do things that you did with adaptive control that's called ISIG. So go back to the RT Tracks program and the ROADS and OPAC and COP algorithm that you guys are studying, and use those. And Yiheng, a shout out to you, he really modified the COP algorithm to work for 8-phase intersections or more general intersections. Then the other part that was really important, and sort of the early potential for doing this, is really given priority to different kinds of vehicles. And one of the reasons I say it's early, because we can equip fleets of vehicles, transit vehicles, trucks, emergency vehicles, while we're developing the technology and getting it into the market and getting market penetration of regular vehicles. So there was some work that was done with Darcy Bullock at Purdue and Tom Urbanek from Texas A&M on a project called NCHRP 366. And it was really to go back to the controller and look at the logic of the traffic signal controller, because we hadn't had a change in like 60 years. And was it the right thing? Are we doing it right? What improvements could we make? And that work transitioned into a standard called NTCIP 1211, signal control and prioritization. We've added a hierarchy that I talked about that's there, and a couple of my PhD students, Ching He and Mehdi Zamanapour, really dove into the priority algorithms, and then a smartphone application for PEDSIGs, and I think this is available through CAPTCH now with Sarikos for Ravi's work. I just want to give you a basic idea about how this works. I think everybody here probably understands, but I want to do this. So when one of these vehicles that's eligible for special treatment at the traffic signal approaches an intersection, like EV, freight, transit, platoon, strings, whatever it is, and they enter the range of the radio, and they get the map information, then the map and the wave message tell them what channel to go talk on. So I'm on the map, I figure out where I am and where I want to go on the map, and I send a request message, a signal request message, to the intersection that says, I want to go through the intersection on this approach and I'll be there in 23 seconds. 35 is better, 40 is even more, 50 is even better than that, because the more advanced time you give me, the more I can do things with the traffic signal to accommodate those requests, okay? The infrastructure then sends back a signal status message that says, here's your request you just sent me. I'd like to acknowledge that I've received it, and I'm going to serve your request, all right? And here's all the other requests that I've received. Now, a normal vehicle, a transit operator, doesn't need to know that information. A fire truck operator might need to know that information, that there's other fire trucks coming from different directions, okay? So then the vehicle passes through the intersection. It may update its request if its travel time changes for one reason or another, passes through the intersection, it cancels its request, and the intersection goes back to other priorities. And so I'll talk a little bit about how all this works, because being at a university, I get to go into those details where normally I don't get to. But I did want to list priority requests. There's lots of different kinds of vehicles that could ask for priority, right? As a matter of fact, every car could eventually ask for priority, but in the beginning, emergency vehicles, transit, trucks, pedestrians, coordination is a form of priority. Most people don't think of it that way, but for the traffic engineers in the room, I'll ask you this question. If you coordinate a traffic signal, what do you want to do? You want to get a green at a certain point in time, so a group of vehicles, a platoon, can progress through the signal and move down the street. If you're going to give priority to a transit vehicle, what do you want to do? Get the signal green at a certain point in time so a vehicle can progress through the signal and go down the street. So by definition, they're the same. So I should treat coordination just like I treat priority and make it one of the things that I can decide who's more important. And then platoons of trucks, strings, even queues could be given priority. So one of the things we have to accommodate is how do we deal with queues. Queues could just be a priority request that says I need service now because I have 20 vehicles queued, okay? This is kind of a busy slide for this format. It's the architecture. The thing that's kind of important is in the bottom, in the gray boxes, those are all the travelers that are in the network. And the sensors that go with them, like the loop detectors or video detectors. And on the right-hand side, we have the vehicles. Some are equipped and some are not equipped, right? Left-hand side, we have the pedestrians. Some are equipped, some are not equipped. We're going to have to live with the fact that we don't have everybody for a very long time. But if they are equipped, then they have onboard equipment, and there's roadside equipment, and the roadside equipment is connected to something that's right in the middle there that we call a MITS roadside processor. If I was smart, I'd go change my slide and call it an edge processor so that I could be with the current technology, right? But it's a processor where we can process all this data that we're getting, okay, that's there. And then we have the nomadic devices and things that are there. Again, another busy slide, but what we've really done in MITS is we've broken down the functionality into groups of software components that we develop that work together to solve the problem. So there's some message transceivers that send and receive messages. There's a priority request generator that's on the vehicle that sends a request to the priority request server that's on the MITS roadside edge processor that's there. Once we get all the requests from all the vehicles, then we solve a priority problem that I'm going to talk about today. We can observe performance. We can monitor where the vehicles are and capture their trajectories. We call that trajectory aware. I used to call it trajectory tracking, but the federal government reminded me we are not in the business of tracking vehicles, so we're just going to be aware of them. Okay, good idea, I like that. Okay, and then we use that data for performance measures, and then that can feed into an adaptive control component, and then we have to affect what happens on the traffic controller, we have to broadcast, map, and spat, and so on. So, okay, so the people at Purdue will recognize this intersection. This is in Noblesville. This is an intersection that Darcy Bullock used when we did our NCHRP 366, and we made this slide back then, and I've just continued to use it because it's a great way to tell the story. This is so that you understand how traffic signals work. I spent a little bit of time in industry, about 6 years, and one of the products our company produced was software for traffic signal controllers. And one of the phenomena that used to happen is we would fix it. And that means we would break something else. It was a set of rules that we used for how a traffic signal was supposed to work. There was no mathematical theory behind what was there. And that bothered me a lot, but in industry we didn't have time to sit around and come up with mathematics. So when I came back to academia, that's where this idea came from. So I'll just tell you how a traffic signal works real quick in case you don't know. So we start off in, say, phases 1 and 5. It's called a dual ring 8-phase controller. It's the basic control used in North America. And so maybe those are the left turns there on the north-south approaches. Okay? Oh, good. We got the update of Adobe Acrobat. Okay, so after a while, maybe for some reason, like there's no cars making one of the left turns, maybe the second ring will advance to phase 6. So now we have the through and the left. Okay? And then after a while, maybe because there's still cars there, but we get to the max amount of time, that ring moves on to the other. So now we're in phase 2 and 6. There's a barrier down the middle that says you can't cross the barrier unless both rings go at the same time because you're moving to the conflicting phases of traffic. So we're going to jump the barrier and go to the left turns that are on the other side. Okay, we're going to time those phases for a while for whatever reason. Maybe one of them moves on and maybe the other one moves on. And then we're going to repeat the process all over again. And that's really the core of how a traffic signal works. There's lots of things related to coordination and other stuff that go on top of it. But if you understand this part, the core is really there. And so if I want to look out over the future and I want to optimize what's going on there, what I really need to do is put this in a structured framework with some simple mathematics so that I can understand what's there. And so this is called a precedence diagram. And if you've ever done project management and you've done a Gantt chart and critical path method, this is a precedence diagram. I have to time phase 1, which is shown over here as the very first phase on the top, for a little bit of time before I can time phase 2. They're in the same ring at the top. And then I got to time phase 3 in the bottom, or phase 5 in the bottom ring, and phase 6, and then I've got to come back to that node, which is the barrier point, and then I go on 3 and 7 and 4 and 8 and so on. And so if you really use your imagination, you can stretch and compress this precedence graph. And you can look at, this is a 2-cycle model, you can look at 3 cycles and 4 cycles, that goes out into the future, right? Each one of the phases has a few complications. First of all, there's a minimum green time. Traffic engineers don't like short mins. This is what happens if you have a really short min. You turn the light green, 2 seconds later you turn it yellow, and one car gets rear-ended by the other. Right? Because the one car says, yellow, I can stop, I barely started moving, right? So we have to have a certain amount of minimum green time for safety, right? And then in the middle of this other precedence graph that's embedded in that phase, we have the extension time, maybe a signal control priority extension, right? And then those pesky pedestrians, or the transit people call them customers, I don't know how you should look at them, right? But they're really important travelers and they're quite vulnerable in the roadway. Somebody pushes the ped button and they have to get a walk interval for some amount of time. Not very long usually, but for some amount of time, depending on how many pedestrians that are there. And then it goes into flashing don't walk, which we have to let 94% of the resident population cross the street during that time. So we're regulated on how much time we have to give the flashing don't walk. And then it goes into don't walk, and then we need to have the yellow change interval and the red clearance interval, and we can argue about where the arrows point and everything, but I like that argument, okay? And so that gives me some constraints as to what we have to do. And then, to make it even more complicated, we don't use all the phases all the time, and we don't do things, so there's flags about omitting phases and flags about recalling phases, and then we got to put the priority requests and everything in there, and then the traffic engineers like to change the timing, so the 7-second min time becomes 15 because somebody called the city and complained, and so we've got to be able to deal with all that data. And so what I want to do, the new thing over the traffic, and it's not new anymore because we did this a long time ago, but is to throw in a priority request. So this arrow that I'm showing here is a request for phase 8. And it says at time 38, so I'm assuming right now I'm at time 0. At time 38, I want to serve phase 8 so this vehicle that's requesting priority could get served. Okay? So where's phase 8? Well, there's one phase 8 down here in the bottom of the first ring, or the second ring of the first cycle. There's another phase 8 out here in the bottom of the second cycle, right? And there's my request. So if I mark these times, I could measure the delay if I don't do any stretching and compressing of the graph. And that's the whole deal, is I've got to stretch and compress the graph. Okay? And I could get priority from all kinds of things. So there's the kinds of delays. As a matter of fact, I could get all kinds of priority requests from all kinds of vehicles. Now, if you're one of those people that says, wait a minute, I've seen the priority for emergency vehicles. It's a little flashing light that comes on and everything. And the traffic signal controllers of today serve one at a time. They don't have a mechanism for saying, oh, there's 3, 4, 5 coming. They don't look at what they're currently doing to make their decision about what to do next. They have an algorithm program that says, if I get a preempt request, go do this. Okay, now I know that people are evolving and there's some better things out there, so if there's anybody watching and you're like, no, my company does it better, congratulations, I'm glad you're doing that. So now I want to take that idea, that model, and I want to put it in an optimization framework. I want to minimize the total priority delay. I want to have some consideration for the other vehicles that are out there. I want to be subject to the precedence constraints, the phase duration and interval constraints, the service constraints, and all those flags and everything that are out there. So we have some decision variables. How long should the phase be? The green time plus the yellow plus the red is going to be our decision variable. And should I try to serve the vehicle in this cycle or the next cycle? So I have a couple slides really quick. I'll go through them to just give you, it's easy to write the precedence constraints down. They're algebraic equations, trivial. Okay? It's pretty easy to get the phase duration constraints because if you just look at whether, the next slide shows it better, whether we have walk and flashing don't walk, or whether we have a min we have to serve and you know, the other things that are there, yellow and red, we can put those together and we can get a max green time and a min green time. Okay? Phase service selection constraints are a little bit harder because this is a logic. This says I'm going to serve this in the first cycle. So there's a bunch of theta variables, and then there's a bunch of circles with arrows between them. And those circles with arrows are, say, that phase 8 from before. I could serve it in this cycle. I could serve it in the next cycle. I could maybe serve it in the third cycle. What's best? Remember, I'm going to stretch and compress, and those are the intervals that I'm interested in. And so there's that request, that arrow pointing down, which one of these places am I going to assign it to? And so the cycle service selection becomes important, and we can write those down using some OR tricks that we learn in optimization class with some decision variables. And then the objective function looks really nice because all I'm going to do is, if I'm going to serve that request in the second cycle, is what I've shown on the diagram on the bottom, that's how much delay it'll have. So the theta times the time between when the phase starts and when the request is gives me how much delay is there. And all the OR people in the room are going to go, oh my God, it's nonlinear integer programming problem. It is. I never got really too concerned about it because there's not many decision variables. Okay? But as a good PhD student, well, here's the list of issues that Ching came to me to and said, this is what's wrong with your model. And those are the PhD students we like because they tell us what we're doing wrong and what we can do better, right? We like students to fix things, all right? So that's what Ching did his dissertation on. He came in and said, yeah, your model's all right like this, the precedence stuff's fine like this, but I'm just going to rewrite this in a really nice compact math programming framework that is a linear integer programming problem. Now we can stick it into a solver and we can get an answer really quick. We get answers in a few hundred milliseconds to this problem. Not very big problem, okay? So I can't go to NSF and get a ton of funding because I have a huge problem because it's not that big. Okay, so I just want to talk a little bit about the solution to this problem. So when we finally get a solution, it's a pretty complex, we call it a schedule. And it tells us what we want to tell the traffic signal controller to do. We still want to serve all the vehicles that are out there. We want to give the traffic controller as much flexibility as we can, but understanding the timing is really important. So we get this thing called a phase time diagram. And there's some words that you could read if you want. But the basic idea is this. There's a priority request up there for phase 4, and time is across the bottom. There's ring 1 on the left, and ring 2 is on the right. We have to put them all together. I'm just going to talk about ring 1. And then these red points become the critical serving points. So now, if you've ever done project management, you have the latest starting time of a phase, and the earliest starting time of a phase, to get the task done on time. That's what these become. These tell us if I I have to start by now, or I won't be able to get there, or I can start earlier than that and I'll find my way to get there. But if I start even earlier than that, all the max times are going to max me out and I'm going to get there too early and I'm going to miss it, okay? So we get this little feasible region. And if you think about the ISIG application that I mentioned earlier that Yihang worked on, he gets to fill up and choose the single path through there of what happens to each of the phases so that I can serve that priority request. Because that's the thing that we're trying to get, is the framework and then the decision making in between. So here's a diagram with three priority requests, one for phase 2, one for phase 4, one for phase 3. Here's some timing and some delays and things that go on. Here's a really complex diagram that says with the minimum green times, the yellow and the red, here's where I have to apply holds and force-offs to make the controller do what I want. Now, sometimes traffic engineers get really nervous. They go, you're going to apply holds and force-offs to my controller? Yeah, just like the other equipment you buy and stick in your cabinet does. We just do it through software. I'm not going to tickle the pins and do things in the cabinet, okay? But this lets me realize the timing of that phase. So, okay, how am I doing? Okay. So, take that sort of new framework where we can put together different priorities under different hierarchies with the real structure for what's going to happen at an intersection, and then think about how I might want to assess performance. And so I talked about this earlier, sort of the classical measures that are out there, the local measures that are out there. Right? We need to start doing performance assessment on a bigger scale, not just looking at what happens at an intersection then adding them up. I have to actually confess that over like 20 years, I thought that was the right thing to do. Volume weighted delay was the measure for the network. Turns out not a good measure. Right? We need to look at time in system, and we can get that with connected vehicles. But I'm going to talk about smoothness because I'm more interested in that. And it's funny, this morning in one of the demos, somebody talked about smoothness. And I like this measure a lot. But here's the idea is, think about these speed profiles that I'm showing you here. So in the upper left, it's pretty smooth. Right? The upper right, it's stop and go, stop and go, stop and go. That's not very smooth. Now the one down here on the bottom, is that smooth? There's one little stop and go period, but it is pretty smooth. And the one on the bottom right, it's lots of variation in speed, maybe not very smooth. So I don't really know which one of these is better, right? So what we did is we defined a measure, we called it soft, right? And we just took, and we want a measure of 100 would be really soft, and a measure of 0 would be really not soft. And so what we do is we look at a ratio of the power in the spectrum. If you took the Fourier transform of the speed curve, and if you were a constant speed, you'd have a DC component. You just have one value in the spectrum, right? But as you have more variability, the energy and the variability begins to show up at higher frequencies. Okay, so I don't know if that works in civil engineering or not, but that's the fact. So here's two speed curves, right, going across here. The one on the upper left is pretty smooth. The one on the right is very not smooth. And below them are their FFTs, the fast Fourier transforms. And they show you the frequency content of what's there. And you can clearly see the one on the right at higher frequencies away from 0, there's more energy, right? So if we just take the ratio of those, we get this measure called soft. So if I look at free operation, a free traffic signal being actuated, not very good. This is all the vehicles going through 5 or 6 signals in a simulation model. Then we coordinated the signals and it looks a lot better, and then we just rested in Main Street green and it looks really good. Okay, there are some adaptive systems that just go for the bottom, right? Okay, so now how could I quantify what's there? Well, if I take the trajectories of each vehicles and I take the FFT of each trajectory and I compute its FFT and compute the soft measure, the ratio of energy between the two, 100 times 1 minus the square root of whatever it is, okay? And then I plot those, you can look on the top, you can look in the middle, and you can look on the bottom. And so the average value on the top, I don't know if I put the average values on here, no. Oh yeah, it's on there, it's just too small. 73, the average value in the middle is 89, and 99 on the bottom. So we know that coordinated flow is better than actuated flow along the main street, and we know that resting in green would be really good. So the soft measure correlates with what we think is better flow of traffic. All right, so what happens now if we stick a bunch of trucks in our traffic flow? right? So the red dots that you see on the right are if we have no trucks in the upper left, and then 20%, 40%, and 60%, and we compute the soft measure, trucks have different flow dynamics, right? They really affect the traffic stream in different ways. Automated vehicles are going to do the same thing because they're going to behave differently. They may make it better, right? And we may do eco-driving and those kinds of things, and you can get soft. So this just shows that the box plot at the top, as we've introduced trucks into the flow, we've really disrupted soft, and maybe we need to think differently how we time the signal, right? Maybe it's just not about simple coordination and things. So I just want to show, this is a corridor, MC85 in Maricopa County. On this corridor, there's 2 Amazon warehouses, and there's 19 traffic signals between them. They run a fleet of 40 trucks between these 2 traffic signals balancing inventory, all right? Because they've got inventory here and inventory there, and they have orders to fill, and they take stuff back and forth all day. So the idea here is to do priority at all the signals along this corridor and see how we can do. Now, of course, we plan the project and we get ready to do it, and then they decide to rebuild the corridor, right? So that means they have new pavement. What's the worst thing you can do to pavement if you're a truck? Stop, right? Pavement's a liquid. Stopping trucks, deaccelerating, tear up the pavement. What's the worst thing you can do to the environment if you're a truck? Accelerate, right? So what we really want is smooth flow for the trucks through here, okay? So this is a simulation of that specific corridor looking at the measure of smoothness, and the graph over on the right really tells you that we have a little trouble getting started, but once we get into the flow of the system, we can really smooth out the flow, right? And I think that this is the kind of thing that we need to be thinking of in traffic signals. So we have a test bed in Anthem, Arizona. The green dots that are in the middle are the ones that are operational. We have 11 traffic signals in our test bed. I think it's like, I used to say it's like M-City but out in the real world. I can't say that anymore. You guys have so many good things going on in M-City with the millimeter wave communication, the automated vehicle, the railroad crossing and everything that's there, but we're live traffic. Right? We have those things out there called human drivers and pedestrians and bicyclists that live in the neighborhood. There's about 25,000 people that live there, 10,000 registered vehicles. It's a walled-in living community. They have to go through our signals. So my goal is still to get 2,000 or 3,000 of them equipped with DSRC. We don't have that many. We're adding some signals up and down I-17, hopefully this year. So one of the big challenges that we've had is getting enough connected vehicles. So we recently have a relationship with this company, No Traffic, which Henry, you said you had met them. And what No Traffic is doing is using video radar sensors to track the vehicles. And I'll play this video for you. This is their promotional video. And what they're able to do is they identify the vehicles and they track them, and they send us BSM data. So I went from 0% market penetration to really high market penetration in no time. So they equipped 3 of our intersections in Anthem. So I'm going to have a chance to, first of all, find out how good they are at detecting the vehicles and tracking them and the pedestrians that are walking across the street here, and drive our algorithms that we've developed while we're waiting for the vehicles to come. The last little bit thing I want to say is that it's been pretty exciting because all the green dots are on here are MITS deployments. That we're doing. The 2 gold dots, San Diego and Columbus, are truck platooning projects that actually I haven't talked to these people in about a year, but I think they're still planning to do these. And then the blue one was Minnesota put out an RFP to do something, and I don't know what happened to it. The CV pilot in Tampa is using some of our stuff. And so it's been exciting to see MITS move from an academic research project out into the real world. Second project I want to talk about is the Connected Vehicle Work Zone. This is a project that was funded by the Federal Motor Carrier Safety Administration. And the idea is, can we use connected vehicle technology in work zones to make it safer for freight vehicles? All right, most of the accidents in work zones involve freight vehicles, like 500 and some deaths a year or something. So I don't have the statistics right off the top of my head. But the idea is that as a truck is planning its route, they could be informed about a work zone. When they get close to it, they could be made aware of it. And then when they're entering and driving through it, they could be warned about the work zone. And so really an important part of the work zone, and thanks to CAMP and the work you guys did with the map tool, gave us the ability to develop the map. I was struggling with the application of how we were going to develop a map, especially when the traditional map wasn't really made for doing this kind of work. So in a work zone, in a map message, that you have the number of lanes, and then you have the lane closures and where workers are present. And the tool that CAMP developed lets us go through a workflow to develop the map message or road safety message that can be sent to the vehicles that has the information that's in it. So the first thing that we do is we take that road safety message and we turn it in, we decode it and turn it into a JSON message, and we send it to this ARIES system that Maricopa County and Arizona DOT operate that tells them these are where the work zones are located. Okay, and so you can see these little work zone icons, one's for eastbound, one's for westbound, on I-10 and MC-85. That's where we did our evaluation and testing. Okay, so it tells you what's going on. So that's to inform the driver so they can find another route. But once they're coming into the work zone, we want them to be aware. We want them to be aware about where the lane closures are happening, where workers are present, and things like that. So we use the road safety message, and then we, as the vehicle drives through the work zone, we pop up some alerts, and I'll show you the HMI. But we developed an HMI so we could do demos, but we also feed the data to DriveWise. DriveWise is an in-vehicle system that Swift Transportation uses in their trucks. And so we shouldn't be telling the drivers what they're going to see. Let the company decide to do that, the people that do that. But this is what our HMI looks like. So on I-10, on this section of I-10, we have 5 lanes, and then this particular one, lane 1 is closed. Lane 5 is going to close in 378 feet, and that's updating in real time, and we're currently in lane 2. And we tried to make it look like an overhead sign gantry so that if you glance down at it, you would know what's going on. Shows you the speed limit in the work zone, and below that it shows you the speed of the driver. I don't know who was driving that day, but it could have been me. 64 was a little fast in a work zone. And then the available maps that we've received that are there and some vehicle information. And so is all we've been able to do is demonstrate this. We don't have an evaluation of how it improves safety or anything, but we used all the connected vehicle components, the roadside equipment and the onboard equipment, to make this happen. So one of the other important applications that I always like to talk about, because I'm going to keep doing this until this is a national standard, is emergency vehicle alerts. And so this is a picture of 2 fire trucks that were on their way to a false alarm on March 30th, 2009, Houston, Texas. Houston's dear to me because our company did the traffic signals there when I was in industry. We did for Houston Metro. There was a woman on a bicycle, and she's under that fire truck that turned over. The 2 fire trucks are on their way to a false alarm. The police report says that both drivers of the fire trucks reported that they knew the signal had been equipped with this fancy preemption equipment, and that they were both going to get green lights. And we still don't do green in 2 directions, despite popularity. Okay? And so that's a tragedy. And I told this story once back in about 2010 in Maricopa County, and one of the traffic engineers said, yeah, but that never happens. So I went to the internet and I found 5 or 6 times that it happened. And then I went back last year and I found hundreds of times that it's happened. And then I went to talk to the fire chiefs in Boston at one of the fire chief meetings where all the major city fire chiefs were there, and the fire chief from Chicago said, when we have a fire in downtown Chicago, we send 40 units. These are 40 fire units of young firefighters jacked up on adrenaline, going to a fire, going to save lives, right? They crash. Right? And we have the technology to save these lives. Okay? We could get an alert into the cab of that vehicle using a vehicle-to-vehicle message or an infrastructure-to-vehicle message. So, look, I'm tired of it. We got to stop this kind of stuff. What's the number 2 cause of death for firefighters? Traffic accidents. Thank you. What's number 1? Anybody know? Cancer. They go into burning buildings and they get soot all over them, and they come out and they hug each other and they high five. And hey, we saved lives. We put the fire out, and they ingest all of that. At that firefighter meeting I was at in Boston, there was a big fire in Boston in 1984, and 50% of the firefighters that were in the building that day had passed because of cancer. Right? So my colleague in public health is working on that. Let's work on this. Okay? All right. And then the last thing that I really want to kind of talk about is this cooperative safety awareness, I'm calling it. And the idea is that when we get these vehicles that are equipped with sensors, and we get vehicles that can send basic safety messages, and we have infrastructure sensors in the roadway, and vehicles are driving through, we should be able to compute measures of safety. So many years ago, Doug Getman and I did a project for FHWA where we looked at something called surrogate measures of safety. And we looked at conflicts. And conflicts were not well liked by the safety gurus like Ezra Hauer, right? Because they were judgment based. So traffic engineers, safety engineers stood out on the roadway and said, ooh, it looks like that car swerved to miss an accident, we'll call that a conflict, right? And then there were some measures, time to collision, post-encroachment time, okay, that were defined for conflicts. And so we tried to estimate those with traffic simulation data, and what did we learn? Traffic simulations are awful. Right? The measures are good, but now we can get high fidelity, real-time data about what's going on in the roadway. We can begin to assess safety of vehicles. So there's a group of us from the new Institute of Automated Mobility that the governor of Arizona set up last October, and what his goal is to not only be a place where automated vehicles are being tested, but to develop the technology for this in Arizona. And so Intel and State Farm and Luminar have joined the team, right? Luminar provides a new generation of LiDAR device, and they're loaning us some of these devices to collect data. This is a picture of a LiDAR image from a Velodyne that we took from an intersection, and if I played a little movie of this, I don't have a movie, I have a bunch of slides, you would see pedestrians, bicycles, and cars moving. We can capture the trajectory of these vehicles with sensors. If they have basic safety messages, even better, we don't have to go to all the work to do it, and we can look for conflicts in the flow of data. These are rare events. But when they happen, they might be indicators of potential crashes, right? And there's been studies that have correlated some of these conflicts with the crash rate and the fatality rate at intersections. Left turns are the hardest one. And one of the things that we're observing in Arizona is that some of the self-driving cars are very conservative at taking left turns. They like big gaps. I got to tell you, human drivers don't. And when they see a self-driving car, they tend to go around it. And this is another unsafe behavior. And so our goal is to start collecting data in the network at intersections where human-driven and automated-driven vehicles are, and take that data and compute measures and be able to say, this is safe, this is not. We need to change this, we need to change that, right? Could be how we time and phase the signal, could be how the vehicles operate, okay? But this is an opportunity. And so that's our latest work. We want to share that information. So we all know that in the connected vehicle world, it's the whole reason that we do this. It's the reason you have your center, is we can save about 84% of the fatalities could be eliminated. I don't like the number 37,000, but that's the one that's actually reported for 2018, I believe. It's too round of a number. It makes me feel like there's 8 people out there that died that we're not accounting for. And we know that every life is really important, and we can do something about that. Okay? We can really do a lot for traffic operations, right? The whole inefficiencies that we have in the system are bad. The whole automated driving vehicle thing we could get into, but they need us. Desperately, they need us. Okay? We still have some challenges. One of the challenges is we need to keep the cost and complexity to a minimum. The agencies that are deploying this are not ready to take on millimeter wave radars, right? And these beamforming antennas and things yet. And I really think V2V needs to remain free of the infrastructure. I'm afraid that if we use a technology that requires a base station to do the timing and framing and everything that's needed to get it to line up, that 2 vehicles in the middle of nowhere will still crash. And they shouldn't do that, right? I grew up in rural New Mexico. I drive across the reservation all the time. I don't think somebody's going to put, 100-meter cell towers all the way along the roadway I drive on. Right? It's not warranted. But there's more on Route 666 from Gallup to Farmington, there's more crashes per mile than I think any other road in the country. And so we need to do something about it. So, thank you for inviting me to give the talk. It's been fun. It's been a great day being here. You guys, this is such an exciting place. So it's an honor to be here. Thank you.